to see you back. First, I would like to schedule a few compensation lectures during the upcoming weeks. At the moment, Tuesday at 10 till 12. Okay with you? Is it הוא מתקיים המעבדה?
כאילו לא, המעבדה לא מתקיימת, אבל אם היא חוזרת להתקיים אז...
No, if it returns, of course, if the strike returns, we'll have to schedule compensation lectures after the end of the semester, according to whatever will be decided about the policy of lecturing after the strike. But at the moment, you don't have lectures, so assuming that the strike won't end tomorrow or Tuesday, so we'll have a compensation lecture at Tuesday at 10 o'clock, 10 till 12. Unless it turns out that this room is occupied, we'll do it here. If not, we'll meet here and find somewhere to give the lecture. Okay. What I'm going to do today...
Is it one time or forever, like permanent?
Forever is a strong statement.
So it's just
I'm hoping, well, I'm hoping that the strike will end, but if not, we'll do it next week and then we'll see how we are standing.
So until next week, it's gonna happen. Just
Probably.
oh.
Well, it's better than coming here in mid-July or something too. And I understand that part of you can't be here in July in any case, so... Okay, so... Where did we leave this lecture? We were basically at the point where we tried to consider what happens if we treat electrons quantum mechanically in condensed matter systems. Well, even stronger in lattice systems. Now, we started from a very, very simple assumption, which was throw out the whole concept of lattice, treat it as particles in a box, and then you have no problems solving Schrödinger equation. We get basically the psi would be 1 over the volume times EIK dot R, and the energy is h bar k squared over 2n. Okay, and then we considered, so lovely, so we put in quantum mechanics. We almost put in quantum mechanics because the main effect of quantum mechanics is not directly connected to this fact, not to the wave function, not to the energy, but to other fact that quantum mechanics teaches us, which is that electrons are fermions. Please?
At Pauli exclusion principle.
Exactly. Much more important than all these facts is the fact that we have Pauli exclusion principle, meaning that not all electrons can reside on the same state. They can't occupy the same state. And that makes a huge difference in the whole game. And what we would like to investigate in this lecture is basically what is the influence of the Pauli exclusion principle on the heat capacitance of electrons. What would you expect from classical physics?
Ideal gas, 3 kBTs.
Yes, half kBT for each degree of freedom. You have 6 degrees of freedom for an electron, 3 momentum, 3 space. End of story. That is not what happens. So, before we go into this lecture is heavy on mathematics. So before we dive into the mathematics, let's keep a physical picture. The main goal that we have here is what happens due to the Pauli exclusion principle. And let us refresh what is Pauli, what is heat capacitance? What is heat capacitance?
How much heat you need to put in the system in order to increase its temperature in 1 Celsius or 1 Kelvin?
Basically the change in the internal energy due to the change in temperature. But once we have a Fermi energy, or the exclusion principle, as we have discussed in the previous lecture, if I'm looking on the occupation of states, let's draw it for 2 dimensions, would be the same in 3 dimensions, just with an additional axis. Basically, the possible states that the electron may occupy are a lattice of points in K space. And what is the difference, the distance between these points?
2 pi over L?
Right, exactly. And where is the energy the smallest?
In the center.
At the origin, 0, 0. Of course, because then k squared is 0. So when we fill up the structure with electrons, put in a few more points. First, we occupy the lowest energy states. We fill in more electrons. We'll go to here, then to here. And when we are going to much larger scales, we'll start filling up more and more states. And basically, once K is large, we'll have a circle of occupied states. And this is exactly K for me. Up till this point at 0 temperature, states are filled. Above it, they're empty. Now, let us think what happens when we come and want to add energy into the system. We add, for heat capacitance, a small amount of energy. We change temperature infinitesimally. So, I come to this electron and ask him, do you want to get more energy? Classically, no problem. I'll take it. Here, sorry. If it's enough energy to move over to here, that state is occupied. Pauli exclusion principle. I'm very interested, but I can't take it. The only electrons that can take additional energy are electrons in the vicinity of K Fermi, because this guy can get a bit more energy and hop into an empty state. So the number of electrons that are taking part in the game is not proportional to the number of electrons. It's proportional to the number of electrons in the vicinity of the Fermi surface. So the heat capacitance is much lower. Same for conductance. If I put an electric field and want to move the electrons, gain some momentum, gain some velocity by the electric field, most of them will say, sorry, can't take it. Indeed, almost any property of the system will depend on what's happening around the Fermi surface. And that's the main take-home message of this lecture. It's not that all the electrons are in the game, only electrons in the vicinity of the Fermi surface. Okay. The details of this lecture are on chapter 2 in Ashcroft. And I'm emphasizing this fact in this lecture because, as I said, this is a lecture that has many mathematical details. Could be useful to refer to the book if you missed some detail or I went too fast or whatever. Okay, so first question is, how is K Fermi connected to the number of electrons? Okay. If you'll refresh your memory from the last lecture, I'm sorry it's more than 2 weeks ago, but still I don't want to return to everything from the beginning. We saw that the density of states well, it's not surprising if the distance is 2 pi over L and you divide you have a three-dimensional system, so that's to the power of 3. Density of states is 1 over it. Nothing too surprising. So if I'm looking at some volume of this circle or whatever I have here, it would be V over 2 pi to the 7. Okay, that's all I need to know in order to calculate the connection between K Fermi and the number of electrons. So if I have n, the number of electrons, so the volume okay, whatever. Times the number of states per unit of volume times the fortunate or unfortunate fact that every electron has 2 spin states should be equal to n. Volume times of number of states per volume times 2 is the number of electrons.
Wait, but why do we have to multiply it by the spin? I mean,
Because in each point here I can have an electron with a spin up and an electron with a spin down.
Mhm. But you said that this is the number of electrons in like density of states, right? Volume and then the spins.
So what's the question?
So density of states. So when you talked about density of state, you talked.
So I assume that I have 1 electron per state, but I have 2 electrons per state. Because in each state I can have an electron with a spin up and an electron with a spin down.
No.
And if electrons would have had spin 1,
So we would have 3 of them in the same spot. We would have to multiply by 3 instead of 2.
correct, but completely wrong, because then I would have a boson and all of them could have occupied the same state, because bosons don't care about it. But the thought is correct. If I would have asked you about a fermion that has a spin 3/2, then I would have 4 states and I would have here a factor of 4. Okay, so okay, for me, just by using this connection, gives me the dependence of K for me on the number of electrons, or more exactly on the density. N over V is density.
Can we define Fermi energy or Fermi K in temperature which is not 0 Kelvin, or this is not valid?
That is exactly the hard work that we will have in the rest of the lecture.
So
Because-
here we talk about 0 Kelvin only.
Here we defined it for 0 Kelvin. Now, again, a bird's eye view of what's happening here. If the temperature is much smaller than the Fermi temperature, which I'll define in a moment, this picture is more or less correct. If it's much larger, then the Fermi surface is of no interest, because it tells you that the occupation is very far from 1 everywhere. You have a very high temperature, of course the electrons will move to higher and higher states, and therefore the states anywhere won't have any probability of being filled with occupation 1 or 2, because the temperature is so low. And then you can forget about Fermi. It has no influence. So let's define the Fermi temperature, because that is the relevant scale here. So the Fermi energy, okay, that's the energy of the highest occupied state. So this defines me a scale of temperature or energy for which everything that I told you is relevant. If T is much smaller than T for me, it's very hard to move within the occupied area. I have a good Fermi surface. If it's much larger, so all states are on average almost unoccupied. I don't care about Pauli exclusion principle because it doesn't stop me from moving from a state to a state. And of course I can define V Fermi, which is okay, to get some feeling what are these values for typical metals. Okay, so RS, if you remember something from already a month ago, is of the order of the Bohr radius. We defined it. At the moment, it's not even very important what was the base. That's the typical distance between electrons. 50 electron volt is a large scale. So usually for me, so this is of order of 1 till 10. Typically for me, temperatures are high. Much higher than the room temperature, meaning that most metals in room temperature, the typical relevant temperature is one that the Fermi surface has meaning. You can't ignore it. If we could have ignored it, we wouldn't have been bothered by this whole calculation. Okay, so last thing that we can ask about the T equal, yeah.
What is V Fermi again?
V Fermi, the typical velocity of an electron at around the Fermi surface. Well, you can check it up in Ashcroft, but let me just quote a number here. They're quite quick, huge velocity. Not yet relativistic, which is 10 to the 8, but within 1% of relativistic. So electrons zip around in a metal in a quite high velocity. Okay, last thing that I want to say about I'll use instead of EU, the total energy of the ground state. Well, sum up over all the occupied states. Well, it's always easier to perform an integration than a discrete summation. So we'll switch to an integral. What did I do here? I basically multiplied again the density of states by the volume. This is volume. And the integration just went through the integration, and we'll find out. Here I forgot the 2 again for the 2 states. Why did I get k Fermi to the 5th?
Because there from the integral you get k third, and then you have the k.
Jacobian. Here I had k squared k to the 4th, therefore after integration k to the 5th. And I can translate it to units of Fermi energy. And this is 3/5 E Fermi, or 3/5 kBT. So the Fermi energy also sets the scale of the energy in this game. Okay, one thing that I forgot here. Of course, this is not the total energy. It couldn't have been the total energy. This is the energy per electron. So the
U total is an energy per electron?
I'm taking this and this is E or U if you want. If I divide it by the number of electrons, okay.
It's an average energy?
It's average energy per electron. So, and that makes sense. We have electrons occupying all states here. So we would guess by not doing any mathematics, half of EF. The fact that we have more electrons on as we increase our shell, so it moves it from 1/2 to 3/5. But half is not a bad estimation. Okay, so far so good. We know everything about t equals 0. But as pointed out here, we're interested in the case that t is not equal 0. So just to set a scale, and just plug in numbers for T Fermi. Told you it's pretty high, but let's give so T Fermi is EF over the Boltzmann constant. So this is order of 1, could be squared order of 10. This is 1000, meaning it's a few, for a typical metal, it's a few thousand Kelvin, much, much higher than room temperature. Okay, so if we are considering non-zero temperature, we can assume that although the temperature is not equal zero, it's still much smaller than the Fermi temperature. So we'll use this fact and ask the following thing. What is the energy at a given temperature? What is the dependence of energy on the temperature? The usual things that we are playing with once considering heat capacity. Okay. Now, a very short refresher regarding statistical mechanics. What can we do? Condensed matter physics, we are taking facts from all over physics to understand these systems. What actually determines the occupation of the system at finite temperature? First of all, what does it mean that we say that the system has a finite temperature?
Some average kinetic energy?
Yes, but let's go back to the basics of thermodynamics or statistical
Temperature
mechanics.
is related to the entropy. This is like a
A much more basic and simpler fact.
Kinetic energy.
I can guess now.
What do we assume once we are starting to work with statistical mechanics or...
Canonical ensemble?
Right. We are at
Equilibrium.
equilibrium with some heat bath. Someone can supply or take from us energy. If we don't assume that, we can't use thermodynamics or statistical mechanics. That's what the temperature means. Of course, it means that we have some average energy in the system, but average, if we weren't coupled to a heat bath, the energy is whatever the energy is. We can't lose it, we can't gain it. Once we are at equilibrium with external heat bath, that is no longer true. We can lose energy, pass it to the heat bath, or accept energy from the heat bath. Good. We assume also another thing here. We're not in the canonical ensemble,
Grand canonical.
but we're in the grand canonical ensemble, meaning that we can receive or get rid of electrons into some external bath. Now this, in some sense, is more questionable, because I can't think of a piece of metal that I'm putting here in the room, and it has no source of electrons to get or receive or extract into the environment. Electrons don't hop around in air, or almost don't. So, why do I assume that I'm in a grand canonical situation, ensemble? Two reasons. One, a lot of the experiments that we do in metallic systems have to do with conductance. What does it mean that I'm measuring or passing current or whatever?
Electrons move.
Electrons move, because I have the battery, I have some external systems that I'm coupled to. There's no current if I'm looking at just lump of metal that is not connected to anything. Right? If I don't close the circuit, no current. The second reason is the mathematics is much easier when I have a grand canonical ensemble. And as long as I'm dealing with macroscopical systems, that doesn't make any difference. Once I go down to very small metallic clusters, like in nano clusters or things like that, where there's a difference between canonical and grand canonical may play a role. But this is for a more advanced course. At the moment, we're just assuming that we are in a grand canonical ensemble. What are the two parameters of a grand canonical ensemble?
No.
T and the badly named other parameter, which is the chemical potential. Well, I'm calling it a badly named because it has nothing to do with necessarily with chemistry. It's just the same ways that the temperature defines the average energy per particle, the chemical potential defines the average number of electrons in my system. Okay, so if I have a state so the occupation of a state which for t equals 0 was simply 1 if k was smaller than k for me and 0 if k was larger than k for me. For t not equal to 0, what does that mean? Basically, I should draw here a three-dimensional plot, but it's harder, so I'll just show a one-dimensional plot. The energy as function of states. For 0, temperature it was just a step function. For t not equals 0, very deep, it's still occupation 1. Very high, it still has no occupation. But I have here a window for which the states are in between. They are partially occupied. And basically, this window is of order kBt, because this is an exponential function. If I'm much lower than kBt from the chemical potential, I'm not occupied. If I'm much larger, I'm occupied, and if I'm much higher in energy, I'm not occupied. And this is the crux of the whole affair here. This determines all the physics here. So how do I determine the chemical potential? Of course, from the condition that if I sum up over all the occupations, I should get N. So that's term and the energy of the system of the state times the occupation of the state. What is the occupation? Here. So EI becomes h bar squared k squared over 2m. And as we stated previously, we don't like summations, we prefer integrals. So and if I want to write this in an integral form, would be n equal okay. Here we have the energy. We could have substituted it with k representation, putting in the exponential a k squared. In principle, it's much easier to think about it as an integral over e, not over k. First of all, it's not three-dimensional, it's one-dimensional if we write down integral over e, and it has a simpler form in the exponential. How do we do it? Okay, we can think about it as just as a variable change. We know that e so and here we should replace k squared dk by e write it this way. This is just a variable change, and we end up with the energy yeah. No black magic, just putting in the definitions of a variable change. Sometimes, well, not sometimes, people usually refer to this part of the integral as the density of states. Function of the energy. Okay, so it goes up as a square root. Again, ignoring the constants, it completely makes sense, because as I go to a larger and larger radius, it goes like k squared. K squared goes as e, but the number of states goes as 4 pi times kf, meaning square root of e. So this is just reality check that it makes sense. Okay.
Is there a volume factor that's missing?
Yes. So instead of looking at U, I'll look here at energy per volume. So basically I have to do two integrals. And these are cumbersome integrals. And basically, doing these integrals, we'll spend now some time on doing it. The reason is not to teach you mathematics. The reason is that they pop up in different topics of condensed matter, and once in your life you should see how it's treated. And this is known as Sommerfeld's approximation, after the physicist who invented it. You have actually probably heard his name in other contexts. Perhaps the most known is the Bohr-Sommerfeld quantization of energy states in atoms, basically taking Bohr's theory of a hydrogen atom and taking into it relativistic corrections. So this guy really enjoyed difficult mathematics. So this is Sommerfeld approximation. Okay, so actually these two integrals have a very similar structure. Basically, you have here some function that could be GE simply, no, someone should have, so either GE or E times GE times F of E.
How is it going with the operation?
Excuse me?
The epsilon? Where do we find it in the...
Okay, good question, because should have been. Okay, so I want to see in general what is the solution here. HE, FE. The way Sommerfeld solved this integral, or at least approximated this integral, is by doing the following thing. He defined another function k of E, which is the integral of HE. Well, it's not clear why it helps, but he's allowed to do it. So h of e by construction. Derivative of this will give you h. Okay. So this is the integral we're interested in.
Don't we want it to be from 0 to infinity?
Okay, you know what, I'll define it 0, it doesn't matter, I can define h as 0. Yeah, but okay, fine.
Other side.
What does it mean?
At the moment, it's just these two guys. I want to solve these two guys. I'm writing a general form of this, disregarding at the moment that in one of them I have GE and one of them EG, but take it into account once inserting the appropriate H there. And looking on the solution, just have written down the substitution. Here I have no problem changing the lower boundary from 0 to minus infinity because both I have no density of states below 0 for e lower than 0. It doesn't matter. Just would be a bit more convenient for the integration. And I integrate by parts. I'm left with because at infinity h is 0, at minus infinity it's also 0, so I'm left only with one term, minus, I just put it inside,
אינטגרציה בחלקים.
integration by parts. That's all we did here. Why is this convenient? Why did I do this whole dance? Unfortunately, remember, this is GE, as function of E. there's only a small window around which this derivative is non-zero of order of kt. Therefore, I have a basis to do an approximation here.
Do you mean FE?
Sorry, Fe. The occupation changes only in a very small window of order kt. So basically, when I'm talking about energy, only energies around mu of order kt are in the game. So, can do an approximation on
And Taylor?
I'm just performing a Taylor expansion around mu. Why am I allowed to do it?
Because you have a small area.
Because only in this small area I care about what is the value of k. Anywhere else this term will kill k. So back to my integral. because this is 2n, and it's a good question. Why?
Because it's maybe a symmetric function.
It's
Oh, because it
the asymmetric parts fall off because you are integrating the same with a plus and a minus sign. They fall off, you're left only with the even powers there. Okay, again, if you missed some details, check up Ashcroft. It's all written down there. Okay, so actually the main result is, after all this approximation, I see that I have here a term that doesn't depend on energy at all, the integration. Okay, and then I can usually stop after one or two terms here. And all this is based on this fact. We're dealing here with small temperatures compared to the Fermi energy or the Fermi temperature. Yes?
We put there the Fermi energy to be the middle of this array.
Well,
That's
not exactly, but that's, we have here mu, actually.
Yeah.
We have to first check what is mu. So we go back and do, but now we have the mathematical machinery to do these integrations. Unfortunately, I have already erased it, but I'll define mu by performing this integration. But before I go there, I want to do a couple of more steps regarding this integration. Okay, finally instead of writing a general function k, I'll stick into it the function I'm actually interested in. So, I want to integrate over e, but I have an ugly exponent within this integration, so I'll define x as e minus mu divided by kbt, and the terms here within this the summation are Okay, ugly. Excuse me?
Is it the second?
The second term. The first term is actually extremely easy because I have a derivative integration, so it's f. Problem start here. Okay, one thing that makes life easier, this term I'm supposed to insert at e equal mu. So I can pull it before the integration. It just doesn't depend on e. It seems to, but actually, all these terms don't depend on E. Can pull all these things also before the integration. So, at the end of the day, the integral that I have to perform is okay. Still quite an ugly integral. Let's perform the derivative. Okay.
ריצ'רד, אנחנו לא רואים במצלמה מה שיש אחרי הקו.
רואים
צד
רק את
ימין.
הקו האדום.
Okay.
תודה.
זה לא כזה קריטי, אבל שכחת די.
Where?
על השאלה כאילו של האינטגרל.
That circle.
לא?
לא, פשוט על מה אתה עושה את האינטגרל, כאילו על הדיפסיה.
X. Okay. Said all of it is written in Ashcroft, so if I missed a factor 2 or something here, it's not terrible. The main idea is to get the general idea about the integral. Okay, and now we come to the interesting part, is how to perform this integral. Looks terrible. Okay, and here we pull out of the hat what you have learned in complex analysis. Integration in the complex plane. That turns this integral into something relatively simple. And just for the last quarter of an hour, that was the main purpose of this exercise, to show you that actually we can come out from a very cumbersome and detailed integral into something that is relatively simple to solve. And it shows you the power of complex analysis. And at the end of the day, you'll forget everything about the integration here, but I would like you to keep in mind the fact that sometimes going into the complex plane makes life much, much simpler. Okay, so let's look at this integral and the complex plane. If you remember anything about integration in the complex plane, what is important about the poles? Excuse me?
Poles.
Poles, exactly. Once I have some structure of poles and I can perform some kind of trajectory around them, I'm in good situation. Now, you're usually used to trajectories that go to infinity. Not in this case. Let's look where are the poles.
-1 and
E
-1.
to the x plus 1 goes to 0, or e to the x plus 1 goes to 0.
So pi I.
Multiplication of pi I. So, at the end of the day, like in any case of integration in the complex plane, this is the integral I want to perform. Now, the usual trick in the complex plane is close it around infinity. It doesn't help me because I have poles all the way up. So actually I use here a box trajectory. Sorry, this is not two. Someone should have. So it's something, it's 3. 2 pi is not. So I'm doing the trajectory around y equals 0 and around pi r. So, I'm going from here, this is my integral. This is 0. It's divided by a large exponential. This residue is a double 1, so I end up, and if you're interested, check up the details in Ashcroft. And we'll change here n to k. So, end of story. The first term in our expansion is pi squared over 3 is the fourth term. And in general, so what's important and what's not important? We actually spent a quarter of an hour on determining these factors, right? The whole exercise here was in order to find these numbers. It's good to have them. They are not essential for our understanding. What is essential for the understanding of the physics is this term. We have corrections here that go as t to the square and after t to the fourth. So, if we have already forgotten what was our aim, we started from this type of integral and ended up with the following conclusion. Okay. What is mu? Okay, mu should be determined. And after I determine mu, should calculate the energy. Just wrote in each case what is h and what is h prime. Remember, here I have a derivative and I had epsilon times g. Okay, we'll continue in the next lecture by performing these integrations. Okay, questions? Okay, so see you